Hello everyone, it's 3 o'clock, it's Tuesday, that means it's Tech Tuesday. Today's topic is latency, which is becoming as important as broadband speeds. I'll be right back. Thanks for joining me, Rick Husey here with Z-Quorum for Tech Tuesday. So there's been a lot of talk about broadband speeds as we try to make sure everybody's connected to broadband, and in some cases we say people don't have broadband because the current definition, which a lot of people say is too slow now, is 25 by 3, right? So that's 25 megabits per second download by 3 megabits per second upload. And there's actually quite a bit you can do with a 25 by 3 connection. But again, if it's something below that, they say you don't have broadband. As your speeds get faster, then you can only do so much with that, and it's really latency that becomes an issue there, especially as we look at newer applications. That's the topic today. I wanted to look at a report that I guess it's VITAG is the way they pronounce it, that they just recently put out. I'm going to link to this when I'm done here, but I did want to go through some parts of it and just kind of give you an overview of what it is, and then again I'll link to it. So again, this is VITAG, I'm assuming, and not BTAG, VITAG, Broadband Internet Technology Advisory Group, and it's Latency Explained. So they are a Broadband Internet Technical Advisory Group, and this is a technical working group report that they did on latency. So again, latency is very important. We think about speeds being important, but as we move into newer applications, and even today with the applications we're using, latency is more important for some people than speeds, and we'll talk a little bit about that. So you can see it's a big report, so I'm obviously not going to cover everything, but there's a lot in here. It's very well done, a lot of content, copyright notice. Hopefully they're okay with this. I'm giving them credit, and we'll link to it. There's an executive summary, which I suppose I could go through, but again, I want to cover some of the salient points here and then link to it. So first off, exploring end-user performance. So they say today when people think of an end-user performance, typically it's solely in the terms of throughput at a home's internet connection. So yeah, that's true. So if you look at the ads that are running for your various ISPs in different areas, it's always about how much speed you can get. Is it a half a gig? Is it a gig? And now they're, with a lot of fiber in the ground, they're starting to emphasize the upload speed, and they're also trying to make symmetrical be a thing, an important thing. It's less important because we still need more download than we need upload, but because some can do symmetrical very easily, like fiber connections, they're really touting that. So that's what you hear about. You hear about speed, you hear about whether it's a symmetrical speed or not, but you don't really so much hear about latency. The internet industry's approach for more than 30 years is that simply increasing capacity was the best way to improve performance, and certainly in the early days that was true. I mean, if you think about it, when you had dial-up modems, it was an awful experience, and you had to increase the speed to be able to make that a reasonable experience. Latency can have a much bigger impact on quality of experience. Consistently low latency is critical to the performance of any application involving user interaction, from web browsing to video streaming and everything in between. Now, obviously, web browsing, less important than some other types of user interaction. I mean, when you click to download a web page, it is kind of annoying when you're watching it load, and there's a lot of things that are going on, which we'll see here. There's a lot that's going on when you're loading a web page, but the latency can have an impact. You just suck it up and just wait for it to load, and you can look down in the corner and see everything that's loading on that page, and you're just kind of waiting for everything to take place, and then the page loads, and it might be 5 seconds, 10 seconds, and you can get through it. This measurement methodology and the metrics typically used to describe latency have very little to do with end-user quality of experience. So they're saying also that not only is latency important, but the way we measure it today doesn't really have an indicator of what the end-user would be experiencing, because we're not measuring it in the right way. So examining latency here. Stated formally, network latency represents the time that it takes for a minimal data packet to travel from one network host to another network host. Latency is the component of delay that doesn't vary with message size. So they're saying you just want to basically send a ping, for example. You just ping and see how quickly that goes and comes back. This network delay is what we focus on in this report because of its impact on the application level delay that affects end user experience. The less delay that a network or application has, the more responsive a service will feel to an end user. And again, if you just take a web page, for example, if you click to download a web page and it all pops up pretty quickly, then it's good. If it takes a long time, it's bad. And that's going back to where the speed was important before, because if you were on a dial-up modem if you're on a dial-up modem today trying to download a web page from today that's got all of the calls that it's making back and forth, you would be miserable, right? But that's really not latency. That's more about throughput. So let's see here. And this latency will become ever more so as new cloud applications, augmented reality, or new cloud applications, augmented reality, virtual reality, and other new application classes emerge. So as these applications get more complicated and there's more required to be going back and forth, and that back and forth has an impact on what you're doing, that's much more important. In addition, it's also important to have a consistently responsive service where delay stays consistently low, no matter how heavily utilized a user's internet connection may be. So what they're talking about there is if there's variations in latency, that can also be a problem. Even if the latency is low a lot of the time, but it varies a lot, which is called jitter, then that can be a problem for certain applications. Less so for web browsing, for example. Really not important for web browsing so much as far as jitter versus a voice call, where you don't want that up and down latency, or maybe video streaming. More often than not, end users, and frankly many network engineers, awfully simply just accept latency variation as that's how the internet works, and they tolerate this oddly variable performance. So again, you're looking down at down in the left-hand corner when your web page is browsing or going to a web page, and you see all those things loading, and you're just like, well, this is just the way it is. There's a lot of stuff, and it's going to take a while. For network operators, more generally, understanding the working latency, defined further below, of the network generally involves measuring the latency across multiple network segments, for example, the home network, the access network, the metro core, etc. The latency results reported by the FCC are really what is becoming better understood as a test of idle latency. Such an idle latency test is typically performed by sending a small number of ping or UDP packets from a home to a destination server on the internet, and reflects the average round trip time for each packet to travel to the server and back. However, such a test is typically performed with no other meaningful traffic utilization or utilizing the end user's internet connection at the moment of the test, and it additionally discards the sometimes significant variation in return trip time from one packet to the next, and that would be, again, your jitter. As a result, a measurement of the idle latency does not reflect the end user's real-world latency. So the FCC right now, with things like RDOF money coming out, that's going to require that service providers have a certain latency requirement, and they have not yet, I believe, maybe for RDOF it's established. For the IIJA, that's also going to have a latency requirement. I think on that one, they've not yet determined how that's going to be measured, and there's a lot of input coming into the FCC, and maybe it's the NTIA right now, on how that latency's got to be measured. And this is the kind of thing that they want to be looking at, is do we want to measure it just as this idle latency, or do we need to look at something different like working latency? The difference between idle latency and working latency can be significant, on the order of hundreds of milliseconds. That's the difference between a player losing an online game between a good and bad video conference experience. So they show an example here of working latency over time. So this is where you're not just measuring one packet, but you're measuring packets over a period of time. And you can see here that 30 to 40 milliseconds latency here, but then there are periods of time when you have these spikes where it gets up over 200 milliseconds, and then it'll drop back down again over 200 milliseconds, bumps up really for a short duration up to over 400 milliseconds, again here over 300 milliseconds, but a portion of that over 200 milliseconds. So that is what working latency looks like, and you can see the variation there. The test of working latency typically involves running a throughput test or a large file transfer to fully utilize the connection, while simultaneously measuring the application layer round trip time experienced by that connection. This will show the packet delay when a connection is in use, reflecting real-world performance. So not just a single packet and nothing happening. So you run a speed test, and maybe all it's doing is sending a packet out and back, and you get that idle latency, but you're not seeing what it's like unless you do a more broad test. Working latency tests don't simply report the average latency experience, but instead focus on the maximum, or perhaps the 99th percentile of the latency measurements, along with the minimum value. the best internet connection will have high throughput, high data rate, in other words, low delay, which will be low latency, and consistent delay, low jitter, and low packet loss. So you don't want to be up and down on your latency, and also you don't want to lose any packets, because that's going to increase the amount of time and the number of packets that you need to transmit. Talks about causes of latency here. It says what causes poor latency, and it shows basically the trip that your internet packets are taking. So if you're here in your home, you've got a connection of some kind. It's showing like a wireless connection here, but they're talking about either a wired or fixed wireless connection. Let's say your broadband connection in your home. Plus, in your home, you've got Wi-Fi access, so you could be on your phone or on a laptop that's connected to your Wi-Fi access point, and then that goes out of the home to the access network of your ISP. Then that ISP is going to connect to some middle mile kind of provider. It says here intercity fiber network, that kind of thing. So it's kind of the middle mile. Then you've got your internet edge and peering points, and that's where you get kind of on the broader internet backbone that everybody's sharing and peering with. Those are your largest, just your few largest providers that are all peering, that are all sharing traffic among each other. Then you get back to another intercity kind of network, back to a data center, wherever it is that you're requesting that service that you're requesting. That could be a web server, could be a voice service, it could be Netflix, could be a cloud-based gaming system, those kinds of things. And the total time of a network round trip is made up of 6 main components. So it talks about these transmission time. That would be analogous to your type of connection. So think about a 28.8 dial-up modem versus a fiber connection that's 1 gigabit per second. That's going to obviously, that's the transmission time, and that obviously has been controlled, and we've been making that get better over time. Then you've got propagation time. That's the propagation, or how quickly you can get through that medium, and we basically have a limit there of the speed of light, or the speed of that electromagnetic signals can be sent, let's say in an RF network, or speed of light in an optical network. That's limited in speed. We can't go any faster than that, so we can't really control that. We can do some things to make the most use out of that, to use multiple frequencies, those kinds of things. You know, whether that's through fiber or whether it's through QAM modulation and OFDM, those kinds of things. So we can do some things to stuff more down that medium, but we're still limited by the propagation time. And you've got queuing delay, and this is a big one. So this is buffering delay, and they're going to talk about that in detail, because that really is the biggest factor, they say, as far as what can be controlled and improved on latency. And you've got processing time. That would be your CPUs that are in your equipment, you know, your routers, your switches, I guess maybe also the CPE, and you know that's got to react quickly. But there doesn't seem to be much of an issue with that. Access to shared medium like Wi-Fi channel acquisition delay, those kinds of things. So you're sharing this bandwidth with other people. You're sharing your Wi-Fi network with other things as you're trying to do stuff. That's in there. It's got other overheads like Ethernet, preamble, etc. That would be like your probably media acquisition kind of delays, request and grants, and those kinds of things, I believe is what they're talking about there. This leaves queuing delay. They talk about these things, as I just mentioned. They say this leaves queuing delay as the single largest component of delay experienced by most network operations today. It largely determines the overall time required to complete a network operation. Though for some network technologies, the medium access and the overheads can also play a role. Unlike the speed of light, queuing delay is something we can improve. Talks about congestion-related delays here. Congestion-related delays in computer networks do not occur in the cables. They occur in the packet switching equipment that connects the cables. For example, switches, routers, access points, network cards, operating systems. When a data packet arrives on a piece of switching equipment and the cable on which the packet is supposed to depart is already busy, the data packet has to wait its turn. If there are many other packets similarly waiting, the data packet may have to wait a significant amount of time, in other words, in a buffer, or for example, in a buffer, or it can be discarded as packet loss, which is obviously not a good thing. But sometimes, actually, the systems will use, we'll see here, the systems will use packet loss to indicate that they're congested. So that's one way to communicate back that there's an issue. So they give a good example here of what a buffer is and how that works. So this is the example of a buffer where, again, you've got packets lined up. And so what you've got is an incoming flow. So let's say this is These are all the packets coming in, and again, they can only travel down that. They all travel down that line at the same speed. The congestion is not in the line itself or in the cable. It's at this kind of choke point. So you've got this buffer here. It's kind of an analogy of a funnel. So it's like you're pouring water in this funnel, and as you're pouring the water in the funnel, you're able to accept more data on this end, but it still can only come out the same speed at this end, right? But you're able to at least buffer this so you don't have any kind of drop packets at this point. However, if this eventually does fill up and starts to overflow, that's when you have drop packets, so that's not a good thing. So that's the way that works. And you know, with this buffer can help you get a good experience where even though there's latency, even though these packets are kind of lined up and not going anywhere at this point, the user doesn't necessarily experience that. So it's not like you know, when it goes into the buffer, you're having to wait. The whole point of the buffer is that you don't have to wait. And it's interesting that I used to work in the early 80s for a company that sold a print buffer. It's called a microphaser. Actually, I was the product manager for this for quite a while for this line of print buffers. So you know, this was basically, you know, if you were around at that point back in the early 80s. Let's see if I can open this picture here. If you were around, you can't quite see it, can you? I'll just go back to here. So basically, back then, before PCs and printers. So again, this was the early 80s. You know, like original IBM PC days. If the PC and the printer, if you wanted to print something, there wasn't really a buffer. So if you wanted to print a larger document, and you were working on your computer on, what was it at the time, WordStar or something like that. I forget what it was, Lotus. I can remember the applications. It's something like Microsoft Word today, but it was something else. So if you were going to print your document, you hit print, then you had to wait for that document to print. It's like you'd be hearing, it was a dot matrix printer generally, right? So you'd be hearing this printer going in the background, and you could not do anything. Basically, your computer locked up until that stream of print data hit that. So we developed and sold this thing called a microphaser that was a print buffer. So basically it was, again, here you see there's a reset, ready, error, copy, pause. So you got your front here, and then it's basically a piece of extruded aluminum. You got some ports on the back, and you know, inside was a circuit board that had your controls, but then also memory chips. So the print data would go from your computer into this buffer, into the funnel, and would accept all of that stuff. And in general, the documents weren't real big at that point. There weren't a lot of graphics, that kind of thing. So in general, you know, you could dump your print job into this print buffer, and it would go in there, and immediately you'd have your computer back, and you could start using it. So we sold a lot of these. These were really, really popular. So that's an example of a buffer, for example, for a printer. But it's the same thing in the internet world, where you've got this information coming in, and again, the user does not necessarily, if everything's working okay, the user doesn't notice that this data is being buffered. But if you think about when you go to load Netflix and you start that movie and you see that little circle spinning and you're just kind of waiting for the movie to start, basically that's everything buffering up, right? So you've got a lot of those packets going in this buffer, so that then when the movie starts to play and that buffer kind of goes up and down, you're not experiencing that change, and you're not experiencing the fact that there are packets at time that are stacking up, right? So that's the whole point of that. Now, there are times when you're watching that where this buffer fills up and starts to overflow, and that's when maybe that circle starts spinning again while you're watching the movie. So everything freezes, the circle spins for 2 or 5 seconds or more, and then it starts again, and that's always annoying. And that could be your local connection, but it's not necessarily. It could be the application and the way they're handling the buffering. It could be something else along the network. It's interesting because I have AT&T, so with that I get HBO Max, but I also have Netflix. And I can watch Netflix, and I rarely get any kind of buffering. Once the movie starts, I rarely get any buffering at all during the movie. I can't think of the last time I've seen it stop in the middle. Whereas if I watch HBO Max, I could watch something, and it could stop 5 or 10 times in the middle of the movie. And sometimes I'll get to like 20 minutes. It might be, let's say it's an hour-long show. I'll get like 20 minutes into the show, and then it'll start buffering. It's almost like the funnel filled up, and then it has to drain a little bit, fills up again, drain a little bit. So I think that's what you're seeing there. And it's interesting because AT&T owns HBO Max, and I'm riding along AT&T's network. So I don't know why. I think it's got something to do with the application level kind of stuff and how it handles the buffering, because Netflix is traveling the same exact network. And again, Netflix is not owned by AT&T, so I don't know why HBO Max, but that just happens with them at my house. The presence of a bottleneck link and its buffer is neither good nor bad, so it's not saying this is a bad thing. What's critical is not that a queue exists or that packet marking or loss will occur. It's how that buffer or queue performs and how quickly it can react to changing conditions and communicate that back to the sender. So again, Netflix, for some reason, when I'm watching Netflix, it's doing that much more efficiently, and I rarely have an issue, whereas on HBO Max I do. Latency versus throughput. Latency and throughput are two distinct characteristics of a path between a sender and a receiver, and they are largely unrelated to one another. So latency and throughput meaning how fast your connection is, fast, not really fast, we'll talk about that, but it's not so much speed, but how much you can get through, and then latency, the delay. That said, there are situations in which they can influence one another. Throughput versus speed. And here's where, again, speed is not necessarily, you think about how fast something can go, but it's not really speed. When we describe a link capacity as 100 megabits per second, or 10 gigabits per second, or 1 terabit per second, what that refers to the amount of data passing through a given point, such as a home's internet connection, per second. And for this, we'll use the terms throughput, bandwidth, bit rate, or capacity interchangeably, but they don't use the word speed because it's not how fast, again, the bits are traveling at the speed of light. It's just how much of those bits you can get through. So a good analogy would be, and I mentioned this analogy here, if you've got a highway, and let's say you go to work every day, and during rush hour, let's say it's a 4-lane highway, and it just gets congested at rush hour. Well, and all the cars, they may be going 40 miles an hour. Maybe it's a 70 mile an hour speed limit. All the cars are going 40 miles an hour, right? So that's not good. There's a lot of delay. You can increase the number of lanes, and that's increasing your throughput. So let's say you go from a 10 megabit per second highway to a 100 megabit per second highway. So you're adding a lot more lanes. And at that point, maybe the cars can get up to the speed limit, 70 miles per hour, but that's the speed limit. So let's assume that people are going to not exceed the speed limit, which is unlikely, right? But in this world, we're saying that's our example. The speed limit is fixed, so the packets can only go so fast. So you're not really increasing the speed when you add bandwidth. You're increasing the throughput. You can get more cars down the highway, right? But they're all going to be going at the same speed. You can't increase the speed. So here you can get more packets down through that connection, but you're not increasing the speed of the packets. But you are helping to decrease congestion, right, when you do that, up to a point. But once you get to the point where everybody's going 70 miles an hour, increasing the number of lanes isn't really going to help. And that's why latency and managing this latency is so important. Voice and video conferencing. These are important. So all of these systems are highly sensitive to latency. Video conferencing systems use a variety of mechanisms to compensate for latency, variation, and packet loss. So they have ways to try to manage this. They include implementing a jitter buffer that delays the early arriving packets in order to match the delay of the late arriving packets or later arriving packets. So basically what they're doing is they're saying, okay, we're going to just limit how fast you can go based on the back end and how long it's taking these packets to get through. So for a VoIP application, average network latency does not matter at all. What matters is the 95th or 99th percentile packet latency. Engineers of these systems refer to glass-to-glass delay as being a key figure of merit in the performance of a conferencing system. What they're talking about there as far as glass-to-glass is, for example, my image going through the glass of my web camera to the glass of your screen, that's glass-to-glass. And then my voice going from my microphone to your speakers is not really glass, but that's kind of the glass-to-glass on the audio side. When the glass-to-glass delay is low, the call or meeting can seem like a normal conversation. So if you're talking to somebody over a conference call, it can seem fairly normal if you've got a low glass-to-glass delay. As the delay gets longer, it becomes harder to have a conversation, with speakers often talking over one another and struggling to maintain dialogue. We've all had that experience, right? So low glass-to-glass delay for audio and video is critical for a good user experience on a voice or video conference. So you're on that conference call and everybody's kind of stepping all over each other when they're trying to talk. One person starts talking, another person's talking. It's like, oh, no, wait, you go. And by the time you hear, no, wait, you go, then the other person's already going, but then you're going. So it's just a mess. If you think about, this is really, really easy to see when you've got a newscast and you've got an anchor person talking to a reporter in the field, and they could be in a totally different city. They could be across the world, and wherever they are, that delay gets worse and worse. So the longer that delay, the harder it is. So you'll see a lot of that stepping on top of each other as you've got the anchor person talking to the reporter, or then you've got two guests. That's always really interesting when you've got two guests in two different places, and they're arguing at each other, and they're just talking all over each other, and that's got to do with that delay. It's showing here that you can have a fairly good experience. All users report a fairly good experience if you've got 200, let's say around 200 milliseconds or less mouth to ear delay, as they call it. But as you get past that, it declines significantly to the point where you get up to, let's say, over 500 to 550 milliseconds. Then pretty much everybody reports that as being dissatisfied with that experience. For internet and voice and video conferencing and calling systems, a 56 millisecond delay each way, or 112 milliseconds round trip, makes for a pleasant conversational experience, well below the 200 milliseconds one-way delay limit for users to be very satisfied with a voice call. A 3-second delay each way, 6 seconds round trip, makes for a truly terrible conversational experience. Yes. They talk about multiplayer online games here. Gaming is one of the first applications that was really sensitive to delay, because especially the initial kinds of gaming that people were doing. So on the game, you would load the software on your computer, and you had to have a good, let's say a really good laptop or something like that had really good graphic processing, because the game was, all the graphic stuff was taking place on your local PC or laptop, right? So it had to have a good, powerful machine with good graphics processing. So you're doing all of that hard work on your machine, and then you transmitted that to a gaming server. The gaming server was maintaining kind of a copy of that world up on the gaming server, but it was not processing all of the graphic stuff on your end. Basically, what you're transmitting back and forth to the gaming server was telemetry. It's like, here I am in my world, and I just pulled the trigger, and I aimed it over here. And so you're transmitting some bits back to that server that's then putting that on their main server, and then that telemetry gets transmitted to the person that you're playing against if it's a multiplayer game. So it wasn't that much data being transferred. So increasing the amount of throughput for a user, going from 10 megabits per second to 50 megabits per second, wouldn't really make a difference. It was the latency that was important, because you need to be able to transmit what you're doing very quickly without delay. Otherwise, you're dead, right? So if you go to pull the trigger, then you can have a problem there, because you didn't get it pulled in time because your shot took longer to get to that. So that gaming is very important. Then it talks about modern first-person shooter games operating on a client-server model. Each client maintains a local, that's what this is, a local simulation of the world, and sends state updates to the server so that the actions taken by the player can be shared with the other clients and players. So again, you're just transmitting basically the actions of the telemetry that's going on there. Then it talks about cloud gaming. This allows the game to run on a far lower specification client device. So you don't need the big powerful PC or laptop, because a lot of the processing and crunching is going on in the server. So without the need for powerful graphics processing units on the client side, it increases in internet access bandwidth and decreases in latency. It says increases in bandwidth and decreases in latency makes this approach feasible. So you still need low latency for this, but you need a lot more bandwidth as well, because you're transmitting basically a lot more graphics back and forth from the server to the client. Cloud gaming applications are more bandwidth intensive than traditional games, because they have to transmit high resolution video at high frame rates. And it was talking about some of the things that can happen. Where was that in here? Oh yeah, so it's actually, I didn't highlight it in here, but there are things called rubber banding, and this would be on your first-person shooters. Let's say, even if you're just transmitting telemetry, rubber banding is the appearance that a character is moved to one location and immediately snaps back to another. Another is the perception that some players can shoot around corners. In other words, your player is shot, even though from your point of view, you had moved around a corner before the shot was fired. So you move around a corner, and then bam, you're shot, because the telemetry did not make it fast enough to signal where you were at the time. A third is the peeker's advantage, whereby somebody peeking around a corner can see their opponent before the opponent sees them. So you peek around the corner, you can see them, but their latency is worse, so they can't see you, kind of thing. So similar to video conferencing applications, the client needs to implement a jitter buffer in order to provide smooth video playback or playout. Web browsing, again, web browsing I think is less important as far as latency, but it still can be a bad user experience if the latency is bad. Browser often needs to download data from multiple servers, for example, fonts and image servers. There's targeted advertisements, there's databases and authentication systems that you may be using, personalization engines. The current traffic load on a site can impact that, so how intense that site is, what kind of stuff it's using, like images, scripts, JavaScript, videos, and more. It says compared to a 9600 baud dial-up modem and a 10 megabit per second internet connection, obviously the 10 megabit per second internet connection will load the modern web pages faster. And 9600 baud, I mean, that's slower than when I started. I started, it was 14.4 when I started in the internet business. But it's been observed that for most broadband users today and internet connection rates that are above 10 megabits per second, we find that we reach a point of diminishing returns, and further increases in throughput yield little further improvement in page loading time. So for the web, what they're saying is, once you get over that 10 megabits per second or so, you can keep increasing the throughput or your bandwidth, but it's not really going to make that much of an improvement on your web page loading times. To view even a simple web page, like a browser has to perform, to view even a simple web page, the browser has to perform multiple sequential tasks requiring multiple network round trips, and you can see those here. You got your domain name service, so you got to go out and request the actual IP address of the domain that you're typing in. So you type in, Microsoft.com. It's got to go out and look up the IP address, come back, tell you what it is, and then you go off. So there's lots of back and forth here. You've got to establish your TCP connection, and that might be, usually it's a secure connection, HTTPS, so you've got to establish that. That's another round trip. You've got GET requests for one or more of these things, so you're going back and forth. And it says loading even a simple web page can easily take 5 or more sequential network round trips. In addition, since most web pages today are not simply text, but also involve images, style sheets, fonts, scripts, etc., if they come from different servers, fetching those resources can take an additional 5 or more sequential network round trips each. And I don't know, again, I'm dating myself here, but I remember at one point we sold a service called Dial Express. It was a dial-up accelerator. And if I remember, it was a proxy. We had a proxy server, and then there was a client that you loaded, and then you set your proxy settings. I think you set your proxy settings on your end. So we had a proxy server. You'd set your proxy settings and point your browser to that, and then all of the data would run through us, which you would think would make things take longer. But basically, what we did was we stripped out all of the images. So if you wanted to, we could do that. We could strip out the images, but we actually reduced the quality of the images, because a lot of times, when you're loading a page and it's got 7, 8, 10 images, some of them are ads maybe, and those kinds of things, you don't necessarily care if that image is perfectly, you just want to be able to see what it is, right? So it would reduce the image quality, which reduced the number of packets that were being transmitted, and it improved the experience. So if you're on a dial-up connection, you could load the page a lot faster. The images will load up quicker, and they'd still be very recognizable. They'd just be a little bit lower resolution. So, we don't need that today. But that kind of, again, is how we handle those things. Talks about the role of latency on future applications, and this is really why we're heading in this direction, because applications are getting more and more user-intensive and are requiring, let's say, user and server, more of this interaction that needs to be more immediate, and that's why we're needing to get lower latency. Looking to the future, it seems likely that the emergence of very low or ultra-low latency services may enable entirely new classes of applications to be created, and people are already thinking about these things. What if a network-based resource were as responsive or available with similar latency as a locally installed resource? So it's almost as if you are, you got something on your computer and you're just clicking to open a file versus going to a cloud-based drive and opening and downloading a file. What if it was just as fast? For example, applications for self-driving. So you've got autonomous vehicles, autonomous cars, or crash avoidance mechanisms, or require an automated system to react in less than 100 milliseconds. That doesn't seem like, that's not too bad, 100 milliseconds. This means latency of vehicle-to-vehicle communication, directly or through nearby network nodes, or vehicle-to-infrastructure communication must be consistently low before such communication can be reliably used to assist in these applications. So consistent. And I don't know about trusting myself in a car that something has to be consistently low latency until I see that really proved. There's a similar strong push to develop ultra reliable low latency applications as low as 1 millisecond in 5G infrastructure. This to support things like human-centric communications in health. And that could be, I think, they're talking maybe something like remote surgery there. Obviously you want to talk to your doctor, and you can do that today through telehealth. But if you're going to do remote surgery, something like that, the doctor is going to be doing surgery on you. You need to have good low latency. Safety, office and entertainment or machine-centric communications for driverless cars. Driverless cars, that's scary. Enhanced mobile cloud services, real-time traffic control optimization, those kinds of things. Anything real-time is very important to have low latency. Virtual reality environments require extensive cloud-based rendering systems with minimal latency to synchronize updates to the images presented in a head-mounted display with the user's head movements. So you move your head this way and everything's got to kind of shift with you very quickly. For fully remote rendering, much of this latency budget is consumed by the motion capture and image rendering process, leaving perhaps only 1 to 2 milliseconds of network return trip time between the head-mounted display and the rendering engine. So before we can get to this virtual reality stuff that's operating over a network, we need that kind of performance. Talks about sources that contribute to latency, and these are things that we already talked about: propagation, buffering delay, and again, that's the important one: switching and forwarding, media access delay. Media access acquisition delay is kind of the grant process where, hey, I need something, and then the server responds, and you got to go back and forth on that. Let's see here. Buffering delay. So again, this is what they really focus on in this. So in general, networking equipment needs to have the ability to temporarily buffer or queue short bursts of traffic that arrive at a rate that exceeds the rate of the output or egress interface. So again, if you think of that funnel, you got to be able to receive more data that's going to exceed the output of that little end of the funnel there. There's the impact that senders and network protocols have on path latency. The manner with which an application sends its traffic can have a large impact on the latency that it experiences. The sender sends its packets too quickly, such that they are arriving at the bottleneck link faster than they can be forwarded. They will cause the queue in the bottleneck link buffer to grow, or that the top of that water in the funnel is growing and growing, resulting in increasing latency for all applications that are sharing that buffer. So the point there is, it doesn't matter what you're having to transmit. You could be not transmitting that much data, but you are still stuck behind that buffer and that growing buffer data content in that buffer. Senders need to implement mechanisms to detect when they're sending data too quickly and then react by slowing their sending rate. These mechanisms are referred to as congestion control algorithms. Unfortunately, the predominant congestion control algorithm today, cubic, works best when the bottleneck link has a deep buffer and it generally keeps that buffer full, resulting in significant latency. So again, if you've got a full funnel, okay, you're still going to have significant latency because you're still going to have to wait until everything gets through that funnel. So there's still a big delay. It might be a consistent delay, but you still got a big delay for all of that buffer content to work through that, and then you finally get out the other end. Tail drop, first in, first out queues. That's like that printer buffer that I was telling you about, first in, first out. So the simplest and most common buffer implementation in networking equipment today is single tail drop, first in, first out queue, or FIFO. As packets arrive, they line up in the egress queue in arrival order, and they depart in that same order. So first in to the funnel, first out of the funnel. Skipping past some of this, you're welcome to read it after. I'll link to it here. Just wanted to get to the kind of key point here. Current and future technologies to reduce latency. So one is to move content closer to users. So they talk about content networks here, CDNs, local cache servers. I remember when we used to sell those to ISPs, is we would sell them, because again, that was to help reduce the amount of bandwidth that they needed to have on their local network, and also to increase the performance. So you put a cache server at the ISP's location, and for content that was constantly, or a lot of content that would be looked at by a lot of your customers, that would be cached. So then customer one goes to a web page or something like that, and the content is then cached in that cache server. When customer two goes to that same location, instead of going off on the internet to that website, they go to the cache server, and they would get that a lot faster. I think that's less, there's so much content is changing so much now. I think ISPs are not doing that as much. Plus they all have bandwidth is not so much the issue now. DNS caching is widely employed to reduce the time to respond to DNS queries. More recently, a new type of so-called network edge compute, NEC, and multi-access edge compute, MEC servers have started to be deployed to offload computation-intensive yet latency-sensitive tasks from client device to the network. So these are more latency sensitive, and again, it's offloading that. So it's a way to identify those things that are more latency sensitive. Then you've got active queue management. Active queue management monitors the queue depth or delay and then sends congestion signals either by dropping packets or implementing explicit congestion notification to try to maintain lower queuing delay. So you can see here that dropping packets is kind of built into the process on some of these things. It talks about explicit congestion notification here, which is a better way to go. Historically, and still common today, the internet has used packet drop or loss as a means of signaling congestion to endpoints. So in other words, again, it's like if you've got that funnel and there's somebody holding the funnel and then there's another person pouring water in the funnel. The person holding the funnel looks at it, and when it starts to spill over, they're like, hey, slow down. So it's like you're waiting until you're getting packet loss before you're communicating to the sender that it's time to slow down. So that's not the best way to go. It says, in turn, endpoints interpret those packet drops as a congestion signal and thus modulate the rate at which they send the traffic into the network. Endpoints additionally need to recover from the loss of data by the network, either by concealing the lost data, for example, in the case of a real-time voice call, recovering the lost data, for example, using application layer forward error correction or FEC, or retransmitting the data in the case of TCP. Thus, packet discard is both an essential congestion signal in this case, at the same time an undesirable impairment for the endpoint application. So it's communicating, it's doing the communicating, but it's not good because it's making matters worse, really, in a way. You're having somebody slow down, but it's also taking up bandwidth as you're doing it. As a result, the network needs to strike a delicate balance between sending enough congestion signals to adequately control congestion and sending too many, thus causing excessive impairment. To address this dilemma, over 20 years ago, a 2-bit field in the IP header known as the explicit congestion notification, or ECN field, was defined in order to allow networks to signal congestion to endpoints explicitly without the need to drop packets. That's good, so you don't need to have that funnel overflow. This technology eliminates the impairment aspect of the congestion signal and thus can provide a latency benefit because the packets no longer need to be retransmitted, and that's kind of a big deal. So all of those packets that are falling on the floor out of the funnel, they need to be retransmitted. Further, since many applications require data to be delivered in order, ECN eliminates the head-of-line blocking phenomenon where later packets are delayed at the receiver awaiting the arrival of retransmitted packets. So again, if you think about video, for example, you can't have all the packets have to come in order. So when that buffer is full and you're starting to drop packets, you've got to wait. So those earlier packets have got to wait on the one that is missing in order for it to get there. I guess the later packets have to wait for the one that's missing, and all is then reassembled and sent to you. So that's another problem with these things. Low latency, low loss, scalable throughput architecture. L4S enables applications to adjust their sending rates to make full use of the bottleneck link in a fair manner without causing the latency and latency variation, or the jitter, that existing applications do. This technology is an evolution of the explicit congestion notification technology that was just discussed. To send immediate signals whenever a queue begins to form. The signal, when fed back to the sender via acknowledgement packets, enables the sender to adjust its sending rate in order to keep the bottleneck link busy without building the queue. So you're trying to maintain that funnel, you're maintaining that queue, and you're not getting to a point where you're going to overflow. That rate adjustment can happen more rapidly than traditional packet loss congestion signaling, and again, you're not having to retransmit stuff. One benefit of L4S is that it is incrementally deployable, so that it does not need to be deployed everywhere before users experience a benefit. So you can deploy that in certain areas, and in areas where it's not deployed, it can use the traditional kinds of congestion management. As the IETF has worked on L4S, it recognized that some applications don't seek to send data at the fastest rate possible. In other words, they're not capacity seeking, but rather they send at a relatively low data rate and thus don't materially contribute to queuing delay and packet loss in the network. These are applications such as multiplayer online games, as we were talking about. It's mostly telemetry, DNS lookups, and voice over IP. While such applications, and you think that voice is actually a lot of data, it's really not. Voice is not that much data. Video is much more data than voice. While such applications are low bit rate and so do not need great capacity, they are sensitive to latency variation, and loss, and thus would also benefit from being isolated from classic traffic in a bottleneck link. This category of latency sensitivity traffic is referred to as non-queue building traffic. So if you've heard of, if you're in the DOCSIS world and you've heard of low latency DOCSIS, which is coming, that is basically what this is trying to leverage. So low latency DOCSIS has got a couple of things that it tries to do. One is it wants to use these non-queue building traffic and put that off on a separate path. So think about a grocery store. So you're at the grocery store and there's all the cash registers there, and you've got people at every cash register that have got full carts. And you've got a carton of milk and some cookies, right? And you want to go home. So if you're lucky, there's an express lane. So that's the idea, is that you don't want to get stuck behind all of these people that have got all of this data or groceries, cart full of data or groceries that they need to get through the cashier. And you've got two items. You want to be able to go to an express lane and get through. So you're a non-queue building traffic when you've got those two grocery items, and you want to be able to go into another lane, an express lane, and check out more quickly. So that's one of the things that low latency DOCSIS does. The other is the media acquisition, the grant process, where you're requesting data and getting an answer back. They're trying to reduce the amount of time that takes as well. So they've got their observations and conclusions in here. The key network attribute for end user quality of experience is not solely bandwidth capacity, but also latency, as I mentioned. Both are important. Idle latency can be important for diagnostic purposes, but does not correlate strongly to end user quality of experience. Working latency is a better measurement of the end user application quality of experience than idle latency. High latency and/or high packet delay variation, jitter, negatively affects the quality of experience of many applications, from web browsing to video streaming, video conferencing, gaming, and more. It's better to have consistently low latency in all working conditions. So again, you can have low latency a lot of the time, but if that varies a lot up and down, that can cause a problem that's called jitter. Like for a phone service, for example, it's very bad to have jitter like that because you're relying on low latency, but then you have these spikes and it's hard for the applications to deal with that. And again, when you have to have all of your packets in the same order, they can't arrive at different times. Like a web page, you can have packets arriving at different times and they build a web page for you, but you can't do that with something like voice or video. Queue management techniques such as active queue management are available, and they're available now, that will reduce buffer bloat in network bottleneck equipment. Recommendations, they got the recommendations on here. The internet community should start to measure and report on working latency in networks and in networking equipment, as this is often as critical to end user quality of experience as bandwidth capacity throughput. So, and I won't go through the rest of this, you can read through that, but that's kind of their conclusion here, is that buffering is the main culprit here. We need to work on that. And it needs, as we do these measurements of latency, we need to look at working latency and not idle latency. So it needs to be measured over a longer period of time, look at the 95th percentile, and make sure that we've got consistent low latency and not something where you're just measuring packets every now and then and no other traffic's going down the network, so you're not really getting a real-time look at how this might be impacting your customer. So anyway, that's, I think this is all things that are taking place now. As I mentioned, low latency DOCSIS is being worked on, and this is going to be affecting everybody. So you'll start to see latency improve, as I mentioned, on a lot of these broadband funds that are being delivered now through RDOF and ARPA. There are latency requirements, and I think there are some measurements where they have to measure it over time with a certain percentage. I know that they delivered this report to the FCC, so the FCC has it, and they've delivered to other industry groups, so they're trying to make sure that everybody gets on the same page here. So this will all be good, and then as we start to get more people connected up to the internet, and as we start to see more of these real-time, very interactive applications that we all want to be able to take advantage of, then we need to get the latency at a point where that can allow for that. So we'll have the speed, hopefully, as we get everybody connected to broadband, and then we need to make sure that everybody has not just low latency, that you might get from a speed test, or that you might get from pinging somebody, but something consistently low over long periods of time with not a lot of jitter, not a lot of variation. And we can all have a good experience, and we can get some of these new applications that have been so interesting out there as well. So thanks for joining me. If this was helpful, please give me a thumbs up on the video. I'd like that. And subscribe to our channel if you're not subscribed. Click the bell and you'll be notified when I am live. I'm live every day. Today's Tuesday, so it's Tech Tuesday, but tomorrow I'll be back with another broadband deployment news. So I will see you then. Bye-bye.